Let's look at problem 261, graph valid tree. For this problem, we are going to provide again a unified solution. First, I'll look at the statement of the problem, and then we look at the method and the main procedure, and finally we give the code and test generic cases. Let's look at the statement. We have a graph of n nodes labeled from 0 to n-1. We are given an integer n and a list of edges, where edges equals ai, bi indicates that there is an undirected edge between nodes ai and bi in the graph. We are required to return true if the edges of the given graph make up a valid tree, otherwise false. So here are two examples. In the first example, the n is 5 and the edges is 4, and indeed they form a valid tree, so the return is true. And in the second example, the number of nodes is 5 and the number of edges is also 5. So there's a cycle, so it's not a tree, so we return false. So the constraints about the problem are the following. One is about the n, which can have an upper bound up to 2000, and the edges can be empty and can up to an upper bound 5000, and there are no self loops or repeated edges. So that's about the constraint. So now let's look at the method and the main procedures for this problem. First, the method we're going to use is the unified method. And the idea and the procedures are as follows. First, in order to attack this problem, we need to notice what is a valid tree. So a tree actually forms a single connected component, and it has n-1 edges exactly, where n is the number of nodes. So this is the first case. Actually, we can use this definition to first exclude some edge cases. For example, if the number of edges does not equal to the number of nodes minus 1, so it cannot be a tree. Second, so we traverse the edges, and it's mimic the process of adding edges. So during the procedure, if we find two edges have the same root, so it meaning that this new edge will yield a circle, so we're going to return false. Otherwise, at the end of this traversal, we're going to return true. So actually, if we want to for some rigor, although it's not necessary, we can check the number of connected components is actually 1. So before we look at the code, so it's maybe good to check some other practice problems like Leetcode 990, problem 547, and etc. So now let's look at the code. So first, I would like to treat the edge cases because this is very easy to deal with. So basically, we want to track the n is the length. If we want to check if length of edges equals n-1 or not. If not, we're going to return false. So next, with this set edge cases treated, we're going to make preparations for the unified procedure. So step 2, make preparations. No actual work done yet. So for this purpose, I'll first initialize a roots directory which track the node and its parents. So for I in range m. So again, so this one is basically nodes and parents. So now we are ready to implement several simple hyperfunctions. Let's see first for the find method, which accepts one argument and returns the root. So this is basically a very simple one. We return I if I equals its parents. Otherwise, we make a recursive call, so on its parents. So this gives us the find method. So next, let's look at the union method. For the union method, it accepts two arguments. And first, I will track their roots using the find function we just implemented. And then we'll check if Ri does not equals Rg. So we are going to union them by setting the roots. So let's set the roots of Rj equals Ri. So that's about it. So now, as a static case, basically I want to implement an extra method called getComponents. So though it's not absolutely necessary in this problem. So for this, we want to check the number of components in the result, in the final state. So we will initialize a dictionary and then we iterate the root. So for key v in roots items, and then we find the root of v, and then we check if root is not in D. We're going to set the value to be the single element set. Otherwise, we are going to update this set by adding this key. So finally, we are going to return the length of D. That's the number of connected components. So with that said, so we are ready to do some actual work. So the actual work basically is we are mimicking the process of adding edges so that we exclude circles. So for ig in edges, so we are going to track their parents, their roots. So find I, find J. So we want to check if they are equal or not. If Ri equals Rg by adding this new edges, a new edge, it means that this new edge will yield circles in the graph. So we are going to return false. Otherwise, we just do the union operation. So just union ij. So that's the actual work. So with the actual work done, we are ready to return. So we are required to return a boolean. So actually, we can return if the length, if the get components equals 1 or not. So that's the full solution to this problem. Let's overview it. First step, we are treating some edge cases by checking the relation between the number of edges and the number of nodes. Then after that, we make some preparations to run the union find procedure. And step 3 is the actual work. So we are checking if adding a new edge yields a circle. If not, finally we are going to return true. Otherwise, we just return false in the process. So now, with that said, let's check several special cases. So let's check the first case. So it's true. And also let's check the second one, which should yield false. So that's it. So for this problem, let's just to yield more meta information, let's print out this D and see what we have. So in this case, the D does not output. The reason is that in the process, we already returned false. Let's check the first example. So you see, this all nodes forms a single connected component, right? So let's look at the generic case. Yeah, it passes the generic case. And actually for this problem, so after we exclude the generic, this set cases, actually we do not need this part. So for this part, actually we can comment out, and then we just need to return true in here. So this will also pass the test. The reason is that once we have included the edge cases and there are n-1 edges, if there are no cycles, these edges must form a tree. So let's try it again. Yeah, that's the solution, and the presentation slightly different in this first and second after we comment out the get components helper function. So I guess that's about it for this problem. Thank you very much.